Hi there. This video introduces a new chapter, which is probabilities. The probabilities is a field that has got its own language, okay, its own vocabulary. Of course, in order to be able to calculate simple probabilities, we will work with simple objects most of the time, but not any time. For instance, we will deal with coins, okay? And coins has two sides that are named tails and heads. Okay, so we will play a heads or tails game. We will work with dice as well. Okay, at singular it's a die, and on plural it's dice. These are six-sided dice. For example, next we can play with a set or a deck of playing cards. So you have to know in English the words are the colors of a deck of playing cards that are in this order: spades, hearts, diamonds, and clubs. Probabilities is a field that contains a lot of singular vocabulary that you will discover little by little along the chapter. So let's have a look now, a little overview of the intuitive notion of probability with simple examples. You need to build an experiment, like, for example, tossing a coin. While tossing a coin, you could be interested by a given event that would be it's a head. And our aim is to calculate or to just tell the probability that this event could occur. It's a head has a probability of 1 in 2. 1 change in 2. Okay? So in a common division, you can tell this fraction 1 on 2 or 1 over 2. But in probabilities, you can say 1 in 2. By the way, the result is a real number that is between 0 and 1. Okay? Here it would be 0.5. So let's see again a simple experiment like rolling a die. In rolling a die, your interesting event could be it's a 1. What is the probability it's a 1 when rolling a die? This probability is obviously 1 over 6 or 1 in 6. So it's true if your die is balanced. Okay, and it's not obvious that the die should be exactly perfectly balanced. So the probability is just a theoretical ideal value. So let's take a little bit more complicated event, like it's even. So you know in integers that there are even numbers, which can be divided by 2, and odd numbers, which can't. So the probability it's even is the probability it's a 2, a 4, or a 6 as a side of the die. This probability is then 3 chances over 6. That is simplified in 1 over 2. So let's change our experiment and let's toss 2 coins. So you can imagine 2 coins in your hand and you are tossing them. At the same time, or one after the other, it will be exactly the same situation. What is the probability of getting 2 heads? So now your intuition could, do you make a mistake? For example, let's analyze the situation. If you toss 2 coins, you got 3 different types of results, possible results. You got 2 heads in the end, or 2 tails, or 1 head and 1 tail. So you could think that the probability of getting 2 heads is 1/3, but it's not. In fact, each coin has a probability of 1 over 2 to make a head or tail. So the chains and the possible events are head-head, head-tail, tail-head, or tail-tail, given the result of each coin. And then among that, there are only one chance over 4 to get 2 heads. And this is the real probability of this event. This chapter is here to explain that kind of things. So let's take a game that is a little bit more complicated, and let's roll 2 dice. If you roll 2 dice, there are multiple possibilities in the end, and you would be interested in the event it's a double. So double 1, double 2, and so on. You must admit that each die has 6 possibilities, and then the crossing of the possibilities of the 2 dice lead to 36 pairs of possibilities, okay? And among these 36 possibilities, the doubles are 6. Double 1, double 2, double 3, and so on, until double 6. So you've got 6 chances over 36 to get a double. So the 2 last examples show us that we had to think about the situation and to analyze the situation, and our intuition could make us wrong things. So now let's take an example a little bit more complicated again. Let's play poker by picking 5 playing cards from a deck of 32. And we want the probability I've got 3 of a kind. 3 of a kind means in my 5 cards, I've got 3 of the same level and 2 others. The probability it could occur is very or not obvious at all. Okay, it's very complicated. You can't use your intuition to find out that there are 12,096 chances over 201,376. So approximately 6% in the end. Okay, with this kind of example, we can see that we need a method. We need an analyze of the situation, and we need formulas. And we need to be sure to use the right formulas coming from the right kind of experiment. So it's not as simple as it appears if we talk about probabilities in general. So to sum up this introduction, a game or a random experiment that is a little bit complicated leads to different types of outcomes, represented here by squares and circles, okay, with different colors. We had to be able to sort them and to count them, and to count only the ones that are interesting for us for a purpose of one given event. So in order to be able to calculate probabilities in every possible situation, we have to be able to make combinatorics. That is the term that is used to count the situations or the elements inside some sets. So the main purpose of this video is to establish a certain catalog of results on sets, so definitions, properties, operations between sets. We have to begin with the beginning, okay? And in the end, we'll be able to calculate probabilities. So let's discover or rediscover sets and their abilities. The first point to begin is a Venn diagram. So you can represent the set as a bag inside which you can put elements. So this almost round thing is a set. Its name is A, and it contains the letter of the alphabet A, B, C, D, E, F. So 6 elements. You can name the set by the use of curly brackets. Okay, if you put elements in curly brackets in mathematics, it means it's a set, and it implies that there is no given order between the elements. Okay, whatever the order, it will be this set. Okay. It's an object that contains these objects. So an element of a set has a definition and a notation. So this symbol is read B is element of A, or B belongs to A. The letter H doesn't belong to A. You can create subsets that are named also parts of a set. A subset is another bag which is inside a bag. So you could take the letters A, B, C, for example, and put them in a bag, and this bag inside the bag A. Then this set is included in A. Okay, it's not an element of A, it's just a subset of A. Of course, a set could be composed with only sets. Then in this case, the 3 sets that appear are at the same time subsets of the global set and elements of the set. Okay, it's not a problem to say that the set AB, for instance, is element of B. The set ABC is not. You can't see a bag inside which there are the letters ABC inside the set B. And the single element A is not an element of B. Okay, it's not alone inside B somewhere. Okay, it's associated with the letter B. So let's discover another kind of situation. We discovered subsets on purpose because now we want to talk about the set of the parts of a set. So if your initial set is E, that contains the 3 letters ABC, the set of the parts of E is the set P of E that contains every possible part of E. That means if you want to think on a bag as for a set, okay, you are taking a bag, an empty bag, and you have to take whatever you want from the set E to put in your bag. So what are the different possibilities? You could say, I will only take one element, for instance, A, or B, or C. Or I want to take 2 elements. So you can take AB, you can take AC, or you can take B and C. Are there other possibilities? Yes, there is another possibility. You can take the whole set of elements of E. So the set E belongs to P of E. Are we finished with that? No. With this example, we are missing something. Our empty bag should remain empty. So the empty set is a possibility among others. And the empty set has its existence, its own existence, and its notation. This empty set is denoted by a circle, that is crosshatched. Okay, so you just have to draw some slash over a circle. So the set AB is an element of P of E, and so on. Little notice that I could make before changing slide is that I knew in advance the total number of elements of P of E before thinking of P of E. I knew that there would be 8 elements inside P of E because I knew that there were 3 elements inside E. So how did I know? Because if the initial set E contains n elements, P of E always contains 2 to the power of n elements. and 2 to the power of 3 equals 8. So if my set E would contain 5 elements, the set P of E would contain 2 to the power of 5 equals 32 elements. And that's a first look at combinatorics. That is the general purpose of the first part of the chapter. Combinatorics mean that you have to be able to count the situations that interest you. For example, if I want to count among the elements of P of E only the number of elements that contains 2 elements of E, so AB, AC, BC, I have to know how to calculate it in more complicated situations, okay, without writing them. AB, AC, BC is not taking long to write, but if E contains 10 elements, and if I want to count the number of sets that contain 3 elements from E, ABC, ABD, ABE, and so on, I don't have to write them all. I have a formula to calculate this number. So that is combinatorics. Combinatorics means let's go inside P of E. And maybe sometimes let's take an order into account that is not present here, okay? The set AB, for example, has no order. But maybe in some situations, the order is to be taken into account. So let's go further with our sets. Sorry. Anytime, if we define objects in mathematics, we have to define operations on these objects. So between them or with something that is outside some kind of real number, for instance. If not, these objects wouldn't be as interested as they are with operation. So let's take an example that is some rich example. Let's take the set of the integers between 1 and 12. Let's name it E. And inside E, I've got 2 possible subsets. The subset A of the even numbers, so 2, 4, 6, 8, 10, 12, sorry. And another subset, the subset of the multiples of 3, that are 3, 6, 9, and 12 here. So B is a subset of E. As for A, you can see that A and B have an intersection. Okay, they cross each other. The fact when defining 2 subsets of a set is that you always create 4 categories of elements in the end. You've got elements that belong to A and to B at the same time. Here 6 and 12. You have elements that belong to A but not to B, that belong to B but not to A, and that doesn't belong either to A or to B. Now, let's define operations between A and B. The first one is the complement of one single subset, complement of A inside E. The complement of A is written A bar, and it's the set that contains all the elements that wasn't in A. So if A contains the even numbers, A bar contains here the odd numbers. Now let's intersect 2 sets. Intersection of A and B will be denoted A into B. It's the set that contains the common elements of A and B, so 6, 12. And we can notice that the intersection corresponds to the logical term AND. If you want as an element to belong to A into B, you have to be even and multiple of 3 at the same time. So if you understood these 2 definitions, you can look for intersection of A and B bar. Okay, so maybe notice that the bar means the negation of the set, okay? It's the contrary of the set. So the intersection of A and B bar, A into B bar, means I want to belong to A and not to B. That are the elements on the left, 2, 4, 8, 10. Okay, and with their description, that are the elements that are even and not multiple of 3. Now, let's define the third and last operation in sets, the union. The union of A and B is the creation of one set that takes A and B together. So that's a set that is bigger than A or B alone. This time, it corresponds to the logical term OR. Okay? If you want that an element belongs to A union B, this element has to belong to A or to B. And it's not an exclusive OR. Okay? It's an inclusive OR. It could belong to both sets A and B. It doesn't matter. Okay? The fact is that it has to belong to at least one of both. Last example here, the union of A bar and B. You want elements that are outside of A or inside B. Okay, so that are the elements that are colored here in the scheme on the top left. 1, 7, 5, 11, 9, 3, 12, 6. You can notice that 12 and 6 belong to this union, whereas they belong to A. But the union of A bar and B doesn't mean that I have not to belong to A. Just if I belong to A, I have to belong to B. Okay, one of the two situations have to be met. So I'm talking about odd numbers or multiples of 3. So that are the very first definitions on operations, and thankfully, these operations, or hopefully, sorry, these operations have properties, and these properties are very magic. The first set of properties are commutativity and associativity. Like in real numbers, okay? If you want to calculate 2 plus 3, you could calculate 3 plus 2. It works in the both sense, okay? For the union, it's the same. A union B equals B union A. So you can imagine, thanks to the former examples, that yes, indeed, it's true. The associativity is true as well. Like for addition and multiplication for numbers, okay? 2 plus 3 plus 5 equals 2 plus 3 plus 5. And for the multiplication is true as well, okay? Here, the intersection and the union have got the same properties. So let's make a scheme of 3 sets that intersect. Let's say A is the blue one, B is the yellow one, and C is the rose one. Pink one, sorry. If you want to talk about this formula in particular, you have to intersect B and C. So the area in my graph is this one. If you want now to intersect A with this first intersection, you want to look at the common part of this intersection and the set A, and the remaining is the central part. You can say or see easily that it works at this side. Okay, A into B is this part, and you want its intersection with C. Okay, what remains is the central part, or with the same result. There is here an equality. Okay, for the union, the result will be the same as well. But the union of the three sets is the global set of the three. So more interesting is the possibility of the distributivity. One operation is distributive on the other, and it works in both senses. And here we've got a property that is not true with real numbers, or even with complex numbers, okay? With numbers, the multiplication is distributive onto the addition. You can expand like that from the left to the right, or you can factor from the right to the left, okay? But if you put an addition here and a multiplication here, you are not allowed to expand. It won't work. You can just take some numbers and try to perform the calculation. You will see easily that it won't work. With the operations of set, intersection, and union, that works in both senses. This property will be important for us because it's related with trees in probabilities and with the situation that is a very common one of two crossing subsets into a set. That is in association with the trees that we can build in probabilities. So you have to take a mental picture here of what I'm going to display in this second graph. Inside a set E, let's say a population, you've got two subsets. Let's say A is women. So A bar around A is men. And B is more than 18-year-old. So around B, you've got B bar, less than 18-year-old. Of course, you've got women that are more than 18-year-old, women that are not, and for men as well. This scheme summarizes this situation inside this population. And you have to be able to name every area that has been created in this scheme. There are 4 areas, okay, that are well divided, that have no common elements between them, okay? So the very central area is the set of the common elements of A and B. Let's say women that are more than 18-year-old. It's A into B, of course. But how would be, or what would be the name of this yellow part? You're talking here about women that are under 18. So A and not B. A into B bar. Okay? Being able to translate a concrete situation with concrete words into this kind of writing will be a very, very useful and helpful for you, because behind all of that we are presenting here, there are oncoming formulas that will be a big, big help for us, and that will help us to summarize an example that would take very, very long to expand with words. Okay, that's the simple thing I have to tell you here. So let's go to the blue part on the right here. If you want to be here, you have to be inside B, but not inside A. Okay, it's a B into A bar, or A bar into B, it's the same. And the fourth bar around all of that contains the elements that are neither in A nor in B. So A bar into B bar. Okay, so of course a tree will show you all that in a very simple way, but you have to be able to name just these locations. So now, what is the purpose of this kind of formula inside this kind of graph? Well, if you are taking, instead of C, the set B bar, you will see that this formula is, yes, obviously true. Okay, and this formula with B and B bar instead of B and C in general will be very useful. So let's see it in details. Let's calculate something with the expanded expression, okay, the right one here. A into B union A into B bar. I can see that there is a common factor inside both terms. So I can factor by A my expression. It's A inter into parentheses or round brackets, B union B bar. So I'm just trusting my formula here, okay? But let's continue. Let's go on with that. What is B union B bar? So what is the set? That is the union between people that are more than 18 years old and people that are not. If you want to unify them, you've got the whole set E. So this expression is A into E. And what is now, in the end, the intersection between A and E, given that A is a part of E? So what are the elements that are at the same time women and people? Well, that's women, that's all. So now let's go back to the graph. You can see in a very easy way that indeed the set A here is the union of those both sets, A into B and A into B bar. It is their union. Okay. So you just have to consider that and to remember the notations, the symbols that we can use to talk about this kind of simple situation. Okay, you've got two kind of categorized people inside a set of people, so let's say elements, okay, in general. The two categories have a crossing, an intersection, and then the first category can be divided into elements that belong to the second and elements that doesn't, or that don't. Okay, so this formula is very, very important for us for the following. And it has a definition. We can say that A into BA and A into B bar are a partition of A. So the term partition is defined this way. A partition is a division of a set into parts, okay, parts that are separate parts, okay, that have no common element. And if you group these parts, you are building the whole set. It's a partition of A. So let's go back to our example to see last set of formulas dealing with operations and sets, the Morgan's laws. Morgan was a French mathematician and established these laws that are in fact obvious, even if you can consider them as very difficult by reading them. So Morgan told us that A and B, so A into B with a bar, a big bar here, equals A bar union B bar. So if you want to separate a bar, you have to change your operation, and it works in the other sense. This writing will be easily seen in our graph, so let's see it. So I'm taking back my previous graph, and I'm just noticing that we didn't see the union yet in the graph. Okay, there are here only intersections. So where is the union of A and B? The union means that you have to group A and B into just one big set. So here is A union B. Inside E, you can be inside A union B or outside. And of course, the outside of A union B can be written A union B bar. But we already named this outside. It was A bar inter B bar. We knew that. So yes, this law is true. A union B bar is A bar inter B bar. Okay? And with words not to be inside A or B is to be not in A and not in B at the same time. So the other formula is true as well, but would be a bit more complicated to see in this graph. So let's consider it's true, okay? But you can try to make a graph and to see that, okay? And you can see that in this graph. To finish in this part of the chapter, let's talk about the notion of cardinal number of a set. We know that, in general, in our chapter, we have to count possibilities in order to calculate probabilities. And we didn't count yet in our presentation of sets and operations. So the cardinal number is defined as the number of elements of a set. For example, if our set is our alphabet, the cardinal number of our alphabet is 26. That's all. That's as simple as that. Okay. The cardinal number of the set of the integers that are from 10 to 20 is 11. There are 11 numbers from 10 to 20. And so on. So it's very simple. You must admit that. But what will appear here are formulas on cardinal numbers. There are three main formulas that are very helpful, and they are associated with the definition of the operation in sets. The first one is a very simple one. The cardinal of A plus the cardinal of A bar equals n. What I'm calling n, it's the global number of elements in the global set E. Okay, so it's a cardinal of E. So yes, indeed, the number of elements in A plus the number of elements outside A equals the total number of elements. You can see in the graph that there are 6 elements in A, 6 elements outside, and 6 plus 6 equals 12. That's as simple as that. The second formula is as simple as the former one, okay? But in the second formula, you're only working inside A. You don't consider what's outside. So it's just saying that A can be divided into two subsets, A inter B and A inter B bar. That's the partition we talked about earlier. And of course, the number of elements in A inter B plus the number of elements in A inter B bar equals the total number of elements of A. That's the second formula. That's all. 2 plus 4 equals 6. The third formula talks about union. Okay, if you want to count the number of elements of a union, you have to be careful. It's not the sum of elements of both sets. You have to subtract the cardinal of the intersection. Why? Because if you are counting the number of elements of A, and in addition to the number of elements of B, you just counted twice these two numbers in A inter B. So if you counted them twice, you have to subtract them once. And the formula will be true in any case. Let's see now another way to represent this kind of situation. Another compared to the Venn diagram. A Venn diagram will be complicated if I'm taking a lot of more examples or elements inside my set E. Okay, a table is a simple way to count the elements into every of the 4 subsets that appear here. Well, there are 4 subsets. There could be more than 4, okay, but in our general purpose in this chapter, there will be 4. Okay, 2 categories that crush each other and that create 4 subsets. So you have to build your table the same way always, okay? You have to use 2 columns to talk about A or the outside of A bar, and 2 rows that talk about B and the outside of B. And of course, every section cross every other, okay? Like in your Venn diagram, you've got A into B. You've got A bar into B. That's here, 3 and 9. So there are 2 elements. They are here, okay? A into B bar. You want to be in A and not in B. So that's 2, 4, 8, 10 here. 4 elements. And A bar into B bar. You want to be outside of both A and B. So it has to be 1, 5, 7, or 11, 4 elements. In a contingency table, you're supposed to only count the number of elements and not put the list of the elements, okay? The fact that these 4 elements are the numbers 2, 4, 8, and 10 is an additional information. But in the purpose of calculating further probabilities, you just want to know how many there are. That's all. You can see that you've got margin frequencies that are subtotals. Okay, its translation is subtotals of the table. Inside B, you've got on total 4 elements. You can see the 4 elements of B on the Venn diagram. And outside B, you've got 8 elements. In columns, you've got a total of 6 elements in A and 6 outside A. And of course, the general total is 12. So contingency table will be seen again in this chapter and will be very, very useful. And most of the time, it very usefully replace a tree. Okay, in high school, you were used to work with trees, always trees. But trees sometimes are traps. A contingency table is the most simple way to visualize a situation like A bar, B bar. So let's make a last comment in order to talk about the union. Okay, this is a contingency table that represents crossings, so intersections. But you can see a union inside that. If you consider the graph on the left, you can see that A union B is the reunion or your union of 3 different subsets. A into B bar, A into B, A bar into B. So it corresponds to 3 cells in the table out of the 4. Okay, only 1 cell remains outside A union B. And it's no surprise, this is the cell of A bar into B bar. That is this outside area. Okay, that's all for now. Thanks for having listened to this video. I hope it has been helpful to you. And now I'm just asking you to perform the exercises of this part of the chapter. See you next time and bye-bye.